Hello everyone, welcome back to CodeMaster. In today's video, we will be discussing sorting algorithms, their efficiency, how they work, and their practical use cases. Sorting is one of the most fundamental operations in programming, and choosing the right algorithm can significantly improve performance. By the end of this video, you will have a clear understanding of which sorting algorithm to use in different scenarios. So let's get started. Sorting algorithms are techniques that arrange elements in a particular order, like ascending or descending. They are fundamental in computer science and are used to organize data for easier access and manipulation. Choosing the right sorting algorithm is important because it can drastically affect the speed and resource usage of your programs. For example, a good sorting algorithm can turn an otherwise slow program into a lightning fast solution. Sorting algorithms are more than just theoretical concepts. They have real-world impacts. Let's see why they are so crucial. Faster search and retrieval. Sorting data can be searched much faster, especially with algorithms like binary search. Data organization. Sorting makes it easier to handle larger datasets, like organizing files in directories or arranging names in alphabetical order. Optimized algorithms. Many algorithms, like those in divide and conquer category, rely on sorted data to work effectively. Real-world applications. Sorting is used in scheduling, prioritization, database indexing, and even graphics rendering. Sorting is everywhere, and knowing how different algorithms work gives you a big advantage as a developer. Sorting algorithms come in different flavors, and we can group them into three main categories. First one is simple sorting algorithm, second one is efficient sorting algorithm, and third one is specialized sorting algorithms. So in first one, simple sorting algorithms, we have bubble sort, selection sort, and insert sort. It is easy to understand but slow for larger datasets. In the second one, efficient sorting algorithms, we have merge sort, cube sort, and heap sort. It handles larger datasets better, but may use more memory or complex logic. In the third one, which is specialized sorting algorithms, we have counting sort, radix sort, and bucket sort. It doesn't compare elements directly and can be super fast for certain data types. Each category has its pros and cons, so understanding them helps you choose the right tool for your problem. Bubble sort, the basic sort. Bubble sort is the simplest sorting algorithm, but also the least efficient. So its concept is very simple. It repeatedly compares and swaps adjacent elements if they are in the wrong order. The time complexity is order of n square. It is very slow for larger datasets. Space complexity is order of 1. It sorts in place, so no extra memory is needed. It has stability and it preserves the relative order of equal elements. Best use case is for smaller datasets or teaching purposes. Its drawback is terrible for larger datasets because of its quadratic time complexity. In real life, you would almost never use bubble sort in production, but it's a great stepping stone to understand sorting concepts. The next one is selection sort. Selection sort improves on bubble sort a little, but still isn't very efficient. So its concept is it finds the smallest element and places it in the correct position, repeating this for each element. So its time complexity is order of n square, still quadratic. Space complexity is order of 1, sorts in place. It have no stability because it swaps elements without considering the order. So best use case is smaller arrays or situations with tight memory constraints. So its drawback is always order of n square even in the best case. Useful for small or fixed size datasets, but doesn't scale well for larger inputs. Next one is insertion sort. It works well for small or nearly sorted arrays. So it builds a sorted array one element at a time, inserting each element into its correct position. Its time complexity is order of n square, which is quadratic, but faster than bubble and selection sort in practice. Space complexity is order of 1, it sorts in place. It has stability, keeps the order of equal elements. Best use cases, small or nearly sorted arrays. Its drawback is slow for larger random datasets. Insertion sort is simple and can be very fast for almost sorted data, making it useful for small or dynamic datasets. Next one is merge sort, which is divide and conquer. Merge sort is a powerful algorithm that uses the divide and conquer approach. It splits the array, sorts the halves, and merges them back together. Its time complexity is order of n log n, very efficient for larger datasets. Space complexity is order of n, needs extra space for the subarrays. It preserves the order of equal elements. Best use case is larger datasets or linked list. It have drawbacks like it requires extra memory, which might be an issue for huge datasets. Merge sort is reliable and has a predictable runtime, which makes it great for big complex sorting tasks. Next one is quicksort, which is the fastest in practice. Quicksort is one of the fastest and most commonly used sorting algorithms. It picks a pivot element, partitions the array, so smaller elements go to the left and larger elements to the right, and then recursively sorts the subarray. For the best and average time complexity, it is order of n log n, and for the worst, it is order of n square. The situation is if the pivot is poorly chosen. Space complexity is order of log n because of the recursion stack. It have no stability because elements can jump across position during partitioning. Best use cases, general purpose sorting works well for larger datasets. Its drawback is can degrade to order of n square in the worst case if the pivot is chosen poorly. Despite its worst case scenario, quicksort is very fast in practice and is even used in many programming libraries like Python sort function. Next one is heap sort. Heap sort is a comparison based algorithm that uses a heap data structure to sort elements. It builds a max heap, repeatedly extract the maximum elements and places it in the correct position. Its time complexity is order of n log n for all cases. Space complexity is order of 1, sorts in place without extra memory. It have no stability because the heap structure doesn't guarantee the order of the equal elements. Its best use case is priority queues or when memory is tight. Its drawback is slower than quicksort in practice due to the heap operations. Heap sort is useful when space is a constraint, but quicksort is usually faster for general sorting tasks. Now we have counting sort and radix sort, which don't rely on element comparisons. First one is counting sort, counts the frequency of elements and uses the counts to build the sorted array. Its time complexity is order of n plus k, where k is the range of elements. Space complexity is order of k for the count array. It's best for smaller integer ranges. And its drawback is inefficient for larger ranges or floating point numbers. In radix sort, it sorts the elements digit by digit from the least significant to the most significant. Its time complexity is order of nk, where k is the number of digits. Space complexity is order of n plus k. It is best for fixed length numeric data like phone numbers or zip codes. Its drawback is it's not ideal for floating point numbers or negative values without modifications. These algorithms are blazing fast for specific scenarios but aren't as flexible as comparison-based sorts. Let's break down the time and space complexity of all the algorithms we have discussed so far. For the bubble sort, the best case is order of n, average case is order of n square, and worst case is also order of n square. For selection sort, the best case is order of n square, average case is order of n square, and worst case is also order of n square. In insertion sort, best case is order of n, average case is order of n square, and worst case is also order of n square. For merge sort, best case is order of n log n, average case is order of n log n, and worst case is also order of n log n. For quicksort, best case is order of n log n, and average case is also order of n log n, but the worst case is order of n square. For heap sort, best case is order of n log n, average case is order of n log n, and worst case is also order of n log n. From this table, you can see why algorithms like merge sort and quicksorts are widely used and why counting sort and radix sort are valuable for certain kinds of data. Choosing the right algorithm depends on your specific problem. Let's break it down. For smaller datasets, insertion sort or bubble sorts are simple and fast. For larger datasets, Merge sort or quicksort handles big arrays efficiently. For almost sorted data, insertion sort can sort with minimal comparisons. For smaller integers or fixed range, counting sort or radix sort are lightning fast. When memory is tight, heap sorts work without extra space. Understanding these trade-offs help you make the best choice for your project. Some real-world scenarios or use cases includes quicksorts and merge sort for databases, indexing, and file system. And for search engines, radix sort and counting sort are used. The heap sort is used for priority queues and job scheduling. And for graphic applications and animation tools, we use bucket sorts or radix sort. Knowing which algorithm to apply in different scenario is a powerful skill for real-world development. So let's wrap things up. Here's what you have learned. Sorting algorithms are vital for organizing and processing data efficiently. Each algorithm has strengths and weakness. Some are fast but memory hungry. Others are space efficient but slow. There's no one-size-fits-all solution. The best algorithm depends on factors like data size, distribution, and memory constraints. The key to mastering sorting is to experiment, benchmark, and choose wisely based on your problem's need. In the next video, we will be starting the searching algorithm. So in the next video, we will discuss about linear search. So if you enjoyed this video, don't forget to like the video, subscribe to CodeMaster for more coding tutorials, and thanks for watching and happy coding.